It seems that humanity has gone a long way since the first people appeared on Earth. We've invented so much cool stuff and developed new technologies. We've risen above other species after having built an advanced civilization. We've come from living in caves and cooking our food on fire to walking on the moon and creating 3D breakfasts. Does it mean we can be considered a Type 5 civilization? Oh, I see you're confused. Let me tell you about these civilization types and what they mean. The Type 1 title is given to species that have managed to harness all the available energy of their home planet. That's why this civilization is called a planetary civilization. They gather and store this energy to satisfy the demands of a growing population. We would need to boost our current energy production more than 100,000 times to get to this stage. And then, we would be able to get control over all natural forces on the planet, like volcanoes, storms, or earthquakes. It's hard to believe, but it's actually a very basic level. You'll see it later. As for now, let's move to a Type 2 civilization. It can use and store energy at the scale of a star system. That's why this type is often called a stellar civilization. Experts have suggested several potential ways to do it. The most popular one is called the Dyson sphere. This hypothetical device could encompass every single inch of a star, gathering its energy and transferring it to the planet. What would so much energy mean for the Type 2? First of all, nothing we know about could wipe out such a developed civilization. Let's say a moon-sized object entered our solar system and was heading towards Earth. No need to panic. We would be able to vaporize it as soon as we noticed it. Or maybe we'd just move our planet out of harm's way. Now, a Type 3 civilization can control energy at the immense scale of the entire host galaxy. That's the reason it's called a galactic civilization. The inhabitants of such a civilization would probably be totally different from the human race. They could be cyborgs, both biological and robotic beings. Maybe there would be colonies of robots capable of self-replication. They would spread across the galaxy, colonizing star systems. And still, these species would be restrained by the laws of physics, unless they figured out how to travel at the speed of light. At first, the scale describing civilization types didn't go beyond Type 3, but later, it was extended, and that's how Types 4 and 5 appeared. A Type 4 civilization knows how to harness energy at the scale of the universe it lives in. This could probably allow its inhabitants to live inside supermassive black holes. In any case, they would need to tap into energy sources we can't even imagine at the moment, using currently unknown laws of physics. And finally, an incredibly advanced Type 5 civilization might be living somewhere out there. If we reached this level, we would be able to manipulate energy both within our universe and other universes. Of course, at the moment, we're a very long way from achieving a Type 5 civilization, but it's not impossible. Assuming our world remains intact, we might continue advancing with every next generation. Then, a day may come when we'd be able to travel anywhere we want in the multiverse. Maybe we'd even use wormholes. Theoretical bridges using space-time that creates shortcuts, reducing travel distance and time. We'd be able to tap into mysterious dark matter to produce energy. And we would find the answers to tons of mysteries about us and the universe. But guess what? At the moment, we're not even a Type 1 civilization. Yep, we're not even on the scale yet. Duh! First of all, we're facing some physical limitations of each type of energy source. Plus, we'd need to balance them not to trigger even more climate changes and not make pollution levels rise. Scientists researching this question have concluded that humanity could potentially reach the level of Type 1. But it wouldn't happen until at least 2371.
Don't hold your breath, but we're very close to hitting a major milestone in human history. Some scientists say the next couple of centuries will be a make or break situation for us. will we be a measly Type 0 civilization forever? Or will we blast off into the stars like the boss-level beings we are? Don't know what a Type 0 civilization is? Let me explain. As our species gets bigger and smarter, our energy needs go through the roof. And that's not just because we all want to keep our hair dryers running, but also because all our fancy machines need energy too. Our transportation devices, factories, and communication tools. The Kardashev Scale is useful in measuring how advanced a civilization is, based on how much energy they've got. So far, there are 7 theoretical levels a civilization can be at, according to most specialists. I'll spare you the Google search. Some scientists have estimated that humans are at a mere level of 0.72. We're not even a Type 1 yet? The scale was invented by a scientist named Nikolai Kardashev in 1964. He created it to help look for signs of life in space through the signals it might give off. His scale has 3 main levels that show the amount of energy a civilization has access to. Over the years, other scientists added many more levels, which are even more advanced. This scale not only shows energy access, but also how much knowledge a civilization has. A Type 1 designation is when a species can gather and store all the energy from a nearby star to power its growing population. This means we need to increase our energy production 100,000 times to reach this status. Some scientists say we could reach Type 1 in 100 to 200 years. But for that, we would need to harness all the energy on Earth. It sounds amazing, but compared to what advanced societies with higher rankings can do, this is just a basic level of control. The next level of civilization is called Type 2. They can control their whole nearby star and use all of its energy. One way we might be able to do this one day is by building something called a Dyson sphere. I'll spare you the technical details, but it's like a giant ball that goes around a star and collects all its energy, then sends it back to the planet it came from. With this much energy, nothing in science could destroy a Type 2 civilization. If humans became a Type 2 and a moon-sized object was headed toward Earth, we could just vaporize it, or even move Jupiter to block it. Type 3 civilizations become energy experts and can travel through the galaxy. Humans who evolve into this type may look very different from us, like machines with both biological and robotic parts. They might even look down on regular humans. Who knows? It's unlikely you'll make friends with a Type 3 person, that's what I'm saying. These humans might also have colonies of robots that can replicate and spread across the galaxy. But there are limits to their travel because of the laws of physics, or at least those that we know today. That is, unless they invent a new way to travel faster than light or teleport through wormholes, which are currently only theories. Kardashev believed that a Type 4 civilization could not exist. That's the reason why he did not go beyond a Type 3 on his original scale. He thought Type 3 was the limit any species could achieve. Some people agree with him, but others think there could be even higher levels of civilization. Type 4 civilizations and up were theoreticized by other scientists. A Type 4, for instance, would be able to harness all the energy in the universe and even live inside black holes. This kind of technology would need to use laws of physics that we don't understand yet and might not even have the resources to discover at this point. Type 5 is even more mind-boggling. This would be a level where beings have the power to control the universe itself. It would also exist in a world with multiple parallel universes. Humans are far from ever reaching this level, but if we take care of our planet and each other, who's to say it can't be possible one day? These types of civilizations would have the ability to travel to different universes and even be able to create our own. They have control over reality, and their population would be so large, it would be, in theory at least, indestructible. A Type 6 civilization is even more powerful. They would have the means not only to create and travel to other universes, but also to control the basic functioning rules of these worlds. They would exist in a lot of different universes at the same time, and they could affect all the laws of physics as we know them. They also exist in many different versions of space and time, with different pasts and futures. A civilization that is categorized as a Type 7 or K7 is capable of traveling and controlling the entire omniverse. The omniverse is a term that refers to every universe, dimension, and reality that exists. This level of power is thought to come from an individual rather than a civilization, as the civilization would have merged into one entity that is all-knowing, all-powerful, and present everywhere. Okay, let's slow down for a bit. Before we reach all these incredible levels, we at least need to become level 1, right? But what would that take? Right now, humans are not advanced enough to be considered a Type 1 civilization because we only use a few sources of energy, like wood, coal, and oil. But there are many other sources out there that we haven't discovered or used yet. We'd need to rely solely on renewable sources, like wind, sun, and water for our energy needs. This energy would be so accessible that you might not have to pay for your power bill anymore. In a Type 1 civilization, energy would be as essential as air. One strategy would be for us to turn natural disasters into something positive. For example, we can use tsunamis to make electricity. We could rely less on construction work and use earthquakes to help us change the land. By controlling the planet's energy sources, we could also control the weather. For instance, if a certain place would be experiencing a drought, we could just send rain clouds to bring it back to life. If we become a Type 1 civilization, we might be able to balance the amount of carbon in the atmosphere and end up controlling our planet's temperature. This means that natural disasters will become easier to predict and less damaging. Additionally, we might even be able to live in places we never thought possible, like underwater, on top of mountains where it's freezing, or in the desert. So how close are we to this level upgrade? A recent study looked at the different ways we get energy, like from fossil fuels and renewable sources. Problem is that each way of getting energy has its limitations. For some, we have limited materials. For others, at least for the time being, the costs are too high. So the team behind this study took a careful approach to make precise calculations. They found that we can reach a high energy level, but it won't happen until the year 2371. This study shows just one way we can become an advanced civilization, but it's also possible that we'll get there in a completely different way. Also, let's not forget, the first rule in becoming an advanced technology is to not become extinct. I know that sounds a bit redundant, but in our quest to harness all the energy this planet has to offer, we also need to protect it to the best of our abilities. Until we manage to travel to the edges of the universe, Earth is still the only place we call home.
So how alone are we in our galaxy? Crickets. Yep, we're mostly alone out here. But are there other civilizations lurking somewhere out there in the depths of the Milky Way? Could they possibly have evil intentions and be a threat to us? Hey, like we need more threats. Well, hey, let's have some fun with this. Some theorists reviewed humans' history and past actions toward one another. No miscongeniality awards there. And assuming they were somehow like us, used this to calculate the probability of space invaders. They determined that there could be 4 evil civilizations in our galaxy. The 4 could be eager for intergalactic domination, or maybe just for a good game of dominoes. They could be highly advanced in technology, or they've only just invented an evil version of game consoles. To understand how advanced these cultures could be and what to expect, there is a way to define their threat levels. A method called the Kardashev Scale analyzes intergalactic nations' possible abilities. With 3 different levels, it reviews the amount of energy a civilization could take from their star, indicating their tech level. This only includes those that have reached interstellar communication. So any other beings out there using, let's say, space pigeons will of course be excluded. Type 1 shows that they can harness the energy from the sun, but only from what is received within their own planet, like solar power panels. Type 2 is where they can use the energy directly from the sun, like through a Dyson sphere. It's used to harness all of the sun's energy, having been built entirely around it. And lastly, Type 3, where civilization can use all elements provided by the galaxy, with the power to not only harness the energy from stars, but also black holes, even the central supermassive one. These levels are important to assess how advanced civilizations could be out there. The Milky Way is estimated to be around 13.6 billion years old. Modern humans have only been around for the last 200,000 years, and we're only a Type 1. It's scary to imagine the time other beings have had to develop. We're considered a bit of a late bloomer in comparison. Earth is, shall we say, late to the party because we're located on the outer arms of the galaxy. Mathematicians posit that more centralized star systems have had more time to progress. Now, with that in mind, how common would other intelligent beings be in the galaxy? With all the life-ending events Earth has survived, it's a miracle to have a planet like ours, and that we would be unique. Or are we? Well, there are 100 trillion stars in our galaxy, and there are up to 200 billion planets, with an estimated 300,000 exoplanets capable of sustaining the kind of life we know about. From those habitable planets, how could we tell which ones have other beings eager to send us an email? No one's had the time to individually count, of course. The Drake equation can give us some rough numbers if we take averages of a few key factors. It breaks down the criteria of how many planets with life are intelligent enough to make communication. The numbers are huge, considering how many stars might have planets. And from there, we distill it down further to those within the habitable zone in the solar system. This zone is called the Goldilocks zone, as it's not too far from the sun and not too close to it. It's just right. We reduce the numbers even further by calculating which of those habitable planets will then be able to support life. And from those random places, the equation takes the probability of how many intelligent beings will be and if they are intelligent enough to communicate. The criteria is complicated, and so it's not an easy equation to explain. But from its estimate, there could be up to 100 million planets with intelligent civilizations. But just like with Earth's history or struggles, these civilizations may also have their own challenges. World-ending events should be thrown into the equation, like asteroids, solar flares, supervolcanoes, and supernova. They could also destroy themselves through technology, like AI dominance or nanotech, or by affecting their own ecosystems and running out of resources, or by just acting stupidly. If we take these into the equation, the remaining living civilizations could be around 15,000. But what could they possibly want from humans? We do have an abundance of rare earth materials that could be of value, ready to be harvested and easily collected. Besides an appealing vast amount of water they could suck dry, hydrogen is a required element of rocket fuels. Though these things aren't exactly rare in the galaxy and could be harvested easier from other closer solar systems or asteroids. Our technology might be intriguing to them. Our range of innovations on Earth, invented while being isolated in separate countries, help provide different technology paths around the world. Other civilizations could have followed a completely different route and didn't learn the importance of many things we have here on Earth, like karaoke. The same goes for applied sciences, where they may have evolved in different atmospheres with different elements. Their science would be mainly affected by that, and ours would provide them with more knowledge. Then, there's one of the rarest things in the galaxy, that Earth can support life. This would be very useful for an intergalactic traveler, rather than going through the long process of terraforming an unlivable planet. Why not just take it? With a cozy outpost, it would be a lovely little holiday destination when they need some time off from conquering other civilizations. Fortunately, they wouldn't be interested in eating us, or probably wouldn't have an appetite for anything on Earth. They would need to have similar biochemistry and require the same enzymes to process the molecules we're built from. Whew. But the most likely thing they would want is to remove any competition. The biggest threat to them is anything that would provide a challenge to their domination. But before you get too frightened by these evil civilizations, this was based on human behavior. It's possible that any beings out there could lack or avoid many of our human emotions. For instance, their capacity for anger might be limited, or they could have evolved without it. They could come from a world with a history so different from ours that they could be overly trusting, making us the bad guys. But again, they may also lack empathy and other positive traits we have. Well, let's hope they only have our nice traits. Luckily, there's a big thing that separates us from everything else. The galaxy is huge, and it takes a very long time to go anywhere, even to our closest solar systems. The fastest thing we've sent into space is the Galileo probe, which travels up to 100,000 miles per hour. Even so, it would take 72,000 years to reach the closest star system, Alpha Centauri. Still, with a newly proposed laser-guided probe that could travel at 1/5 the speed of light, it would yet take up to 20 years to make that journey. On a larger scale, the Milky Way is over 105,700 light-years across. If a civilization was even capable of light speed, it would take them hundreds of thousands of years to travel from one end to the other. With a huge distance between the small number of civilizations, the only successful contact would be through advanced interstellar travel. But to achieve such a long journey, the greater the mass to be accelerated, the more energy is required, so it's not likely anything too large will be sent. But they could travel here very quickly in a small shuttle, using the ability to break cosmic speed laws. They may already be here, watching us closely, or just binge-watching Netflix. They would need very advanced technology, and the number of species obtaining this is theorized to be only 2 out of the 15,000. That means there's a 0.01% chance of evil civilizations capable of visiting us soon. If they do know we're here, and they want something from us, it's likely to take them thousands, if not millions of years to arrive. So, we've got plenty of time to relax.
Did you know that humans are real space people? You were born in space. Heck, even I was born in space. We were all born in space. But for humans to be here on Earth, so many conditions have to be precisely correct that it's highly improbable that we even exist. But we do. First, we, and any other space creatures who might be out there, have to live on a planet orbiting a yellowish white star, not a red star or a blue star. Not a blue star, because they burn out too quickly. In a few million years, there wouldn't be time for evolution to do its relatively slow magic and produce intelligent beings. Blue stars also tend to swell up and turn red when they collapse and explode. It makes it highly unlikely that any civilization could prosper near a blue star. Red stars, which are by far the most numerous kind of stars, don't seem like good prospects for intelligent civilizations to orbit around either. Red stars are so cold and so dim that a planet that could grow a civilization must orbit very closely to the red star, which would expose the planet to intense deadly X-ray radiation. So, though red stars are the most numerous and appear to have many planets orbiting them, red stars are a no-go for hosting intelligent, civilized life like our own. That leaves the yellowish stars, about 10% of all stars. However, an important fact must be met before considering the possibility of intelligent life living around a yellowish star. That fact is that the yellow star must be a third-generation star. Only third-generation stars will contain sufficient chemical diversity to sustain advanced life forms. Each time a star explodes, heavier, more complicated elements are created. The explosion expelled these elements and eventually found their way into a nebula. Gravity within the nebula will gradually form the next generation of stars, and so on. Our bodies need calcium for our skeletons and teeth. Our brains need zinc to help create the electrochemical signals that make us move, feel, and think. Our blood needs iron. Therefore, our bodies need to have formed around a third-generation star, and a yellow one. Amazingly, Earth has all the different elements in the universe, all 94 naturally occurring ones, from hydrogen to plutonium. Maybe that's why we're here. And we have to thank our third-generation yellow dwarf sun for that. Why yellow? Because yellow stars burn very steadily by nuclear fusion without significantly changing brightness over billions of years. If our sun became just 6% brighter or dimmer, Earth would become too hot or too cold to sustain civilized life. Fortunately, Earth is in the habitable zone around the sun. The habitable zone is where liquid water can exist on a planet. But that brings us to the second condition necessary for intelligent life to live in space: the planet itself. Recent studies with the Kepler telescope have shown that 1/4 of all yellow dwarf stars may contain Earth-like planets in the habitable zone around yellow dwarf stars. That figure is somewhat debatable. It might be as few as 1 out of every 33 yellow dwarf stars, but that's still a lot of planets orbiting yellow stars in habitable zones. So let's consider the second essential component for intelligent life in space: the planet itself. The planet that would bear intelligent civilization must have many particular characteristics that aren't easy to come by individually, and even more rare to find in combination. Most importantly, the planet must have protection against the star it's orbiting. Because stars shine by nuclear fusion in their cores, gas in the outer shell of the sun, called the corona, gets blown off into space in what's called the solar wind. Our United States satellites take constant readings of the force of the solar wind, which is mainly electrified, ionized, hydrogen nuclei, along with a smattering of atomic nuclei from the many other elements found in the sun. It's not the atmosphere that protects Earth, it's the magnetosphere that stops or deflects the dangerous solar wind, causing aurorae when the solar wind is attracted to Earth's magnetic poles and electrifies the air of the upper atmosphere like a fluorescent bulb. Without a magnetosphere surrounding it, any planet, even those in habitable zones, would be toasted by a constant rain of ionized hydrogen nuclei from its star. A planet with life on it must have a magnetosphere strong enough to deflect the solar wind. Not every planet in our solar system has a magnetosphere. The gas giant planets, Jupiter, Saturn, Uranus, and Neptune, have magnetospheres, but gas planets cannot have civilizations. Of the solid worlds, only Earth and Mercury have magnetospheres, and Mercury is too weak to stop the solar wind because of its closeness to the sun. Another protective shield that keeps the Earth safe from the sun is its atmosphere. The atmosphere is about 300 miles thick, with most of it concentrated within just 10 miles of the Earth's surface. The atmosphere protects life on Earth from both the sun's ultraviolet, UV, radiation, and X-rays. The gas, ozone, which is 3 oxygen atoms bound into a large gas molecule in the upper atmosphere, blocks most of the sun's UV radiation from reaching the ground. The planet Mars, whose atmosphere is 1,000 times thinner than the Earth's, has no ozone, and the sun's ultraviolet emissions have totally irradiated its surface. A planet must be able to stop the UV radiation from its star, so the specific composition of the atmosphere is critical for any planet to have an intelligent civilization. We've got it, but it is a rare and precarious mix. The planet must have some part of its surface solid to walk and work on. The planet must have a crust. It's pure science fiction to consider underwater civilizations or floating civilizations in the atmospheres of other planets. A planet's crust must have tectonic plates that move. This movement of tectonic plates creates the subduction of the crust. Subduction is when one tectonic plate slides under or over another, bringing the fresh matter to the surface. This renewal of the chemical properties of the planet prevents chemical equilibrium, where nothing is reactive. Earthquakes and volcanoes also contribute to the process of geochemical renewal. That's right, earthquakes and volcanoes are good. Subduction of tectonic plates, then, is another planetary essential for life. Mars doesn't have tectonic plate activity, neither does Venus nor Mercury. Mercury is one big tectonic plate, but there's no ongoing plate activity other than slight shrinkage. One big reason these planets have no life is that there's no geochemical reactivity. because there's no tectonic subduction. And that brings us to the moon. Yes, the moon. To say that the moon keeps us alive may seem like a stretch, but the contribution of the moon to life on Earth is essential. First, the gravity of the moon as it moves through space with the Earth not only makes the ocean tides ebb and flow, it also helps the rotation of the Earth to churn or stir the magma inside the Earth. The motion of the magma inside the Earth, with its high metallic content, contributes to the creation of the Earth's magnetosphere. So, the moon keeps us safe in space by helping Earth become a geodynamo and creating our magnetism. The moon is the largest moon in the solar system compared to the size of the planet it orbits. Essentially, it's primary. Many people consider the Earth-Moon system to be a double planet, but that's another issue. Another thing the moon does that keeps life safe on Earth is to hold the Earth steady. Because the moon is gravitationally locked to the Earth, the moon acts much like a balance pole does for a tightrope walker. Therefore, the Earth doesn't wobble very much compared to other planets. This wobble is called libration. If the Earth wobbled as much as Mars or Saturn, not only would our weather become chaotic, but farming might have been impossible. These rare or unique astronomical circumstances work together to make Earth habitable for humanity. Many other factors are not astronomical, such as evolutionary, biological, and chemical factors required for life to exist on Earth. The probabilities, or improbabilities, are multiplying. Taken all together, we are very, very lucky to be here. In fact, we're so lucky that we may have hit the jackpot. Considering all the possibilities, it's doubtful that anywhere else in the universe is as fortunate as Earth.
Dozens of spacecraft and hundreds of probes take off from Earth and head for our planet's twin sister, Venus. It's about the same size as the Earth and has around 80% of our planet's mass. The temperatures here are too high for humans, and it doesn't have the air we're used to breathing. But we went there because scientists recently found traces of phosphine gas, which suggests that life might be there. Phosphine comes from various microbes and bacteria, so humanity goes on this journey to discover this life. With our technology, a flight to Venus would take 3.5 to 6.5 months, but we finally made it. Spaceships are landing on the planet, and when the first humans come to the surface, they see heat-scorched deserts, lava lakes, and geysers of poisonous acid. And that's it. Scientists miscalculated the radio telescope data. Phosphine never existed on Venus. So we're going back to the rockets, and we're getting ready for a longer trip across our galaxy. The scientists believe that there's at least 36 civilizations in the Milky Way that are similar to ours. They could be living organisms completely different from us. They may have different bodies, different eyes. They may walk and talk in a very different way than we do. But an advanced civilization has several criteria: technological progress and the use of developed communication between individuals. So, these civilizations must explore space, build cities, and be able to communicate with each other as independent species. Let's look at our galaxy and find these civilized worlds. So, the Milky Way is a spiral of 100,000 light years from side to side. If a star is born at one end of it in a super powerful blast, the light from that event won't even reach the other end until 100,000 years later. There's about 100 billion stars, and near each of them, there may be worlds similar to our solar system. Let's try to find these habitable worlds using giant sieves. First, we look for stars that have a lot of iron. Such stars burn at the perfect temperature for the development of life. And the iron in the star system will help form the cores of planets that will be home to another civilization. We sift the Milky Way through our sieve. We see that there are too many stars that fit the description, so we need another filter. Now let's find stars that look like the Sun in this pile. The star must be about 100 times larger than the Earth and 333,000 times heavier. An important criterion is the age of the star. When a star gets old, it begins to expand and turns into a red giant. At this time, it can absorb the planets around it. The life of such a star can end with a huge blast that destroys everything around it. So the star we're looking for must be relatively young. Let's use our sieve again. There's fewer stars, but still that's a lot. Now let's focus on the planets. They should be in the habitable zone of the star. Not too close to a star because then the temperature would be too high for life to be born, and not too far away. Then the planet would just be an ice block with nothing living on it. The temperature of the planet must allow the water to remain liquid. Another filter is the age of the candidate planet. It takes time for an advanced civilization to develop. Based on the experience of Earth, scientists believe that it takes at least 4.5 billion years for any life form to evolve to the human level. So we're looking for planets similar to Earth or older. We use our sieve one last time, and voila! We have 36 worlds where an advanced civilization is possible. Scientists conducted this study and published it in April 2020, based on these very criteria. All that's left is to discover these civilizations and make the first contact. We can detect such a civilization by using radio waves that come from it. Suppose there's a planet A with primitive living organisms on it, millions of years of evolution, and they'll become a civilization with advanced technology. Radio waves will be the way they communicate. Then the whole planet will emit radio waves like a star emits light. And here on Earth, we'll be able to pick up this signal with antennas pointed into space. But there's a problem with the distance between the planets. For example, planet A is 1,000 light-years away from the Earth. When planet A starts emitting radio waves, these signals won't reach us until 10 centuries later. We learned to emit and receive radio waves in 1895. And if the civilization on planet A emitted a radio signal at the same time, we won't be able to pick up that signal until 2895. It'll be the same on planet A. We sent a message in the form of a radio signal into space in 1974. In this signal, we encoded our number system, human DNA, and information about our solar system. If there's an advanced civilization on planet A, they'll be able to receive this signal only in 2974, and we'd have to wait another millennium to get a response from them. Another problem with radio waves is that they don't look like a constant glow on the planet, but like a flare. Radio waves are only used at a certain stage of civilization. At first, it's the primary method of communication, but then we begin to use cell phones, cable TV, and fiber optics. And as technology advances further, our radio wave light begins to fade out. So we only have about 100 years of active radio use by civilization to find it. One day we caught a strange radio signal of an unknown origin. Its characteristics suggested that the signal was created artificially, perhaps by an outer space civilization or a passing starship. Further searches for this signal given no results, and this gave rise to many theories and arguments as to what it really was. It could have been a signal from Earth that reflected off a satellite flying through the sky, or it could have been the traces of a comet a few light years away. But let's assume it was a civilization from outer space, one of those 36 that probably exist. Now we need to make contact with them. So we throw our luggage into a rocket and head out in the direction of our suspected planet. Our rockets can fly at 17,600 miles per hour. That means a rocket could cross the entire United States in just 8 minutes. But even if an advanced civilization lived near our closest star, Proxima Centauri, it would take us about 73,000 years to get there. Even at the speed of light, it would take 4.2 years. So we need to solve the problem of space travel. Our scientists plan to reach about a quarter of the speed of light with a laser. A powerful laser beam from Earth will push a microscopic probe in the right direction. This probe could reach our destination in about 17 years. And in another 4 years, when the signal from it reaches Earth, we'll know if there's an advanced civilization. Another possibility for faster-than-light travel is the warp bubble spacecraft. The spacecraft would have to compress space in front of it and stretch it behind its tail. Then we'll be able to reach any point in the universe in literally a few seconds. But such travel remains a fantasy for us. Perhaps we can get to different corners of the universe through wormholes. They're shortcuts similar to tunnels, but there's one problem. These wormholes might be inside black holes. They're the most mysterious objects in the universe. They're so heavy that even light can't escape their trap. Our spaceships wouldn't stand the tension either. There's also a theory that Earth is unique because it was born under completely accidental circumstances. 4.5 billion years ago, our planet was a block of lava that began to cool and solidify. But its tranquility was broken by an asteroid the size of an entire planet flying by. The collision occurred at such an angle that the Earth was not completely destroyed, but part of the asteroid remained in our orbit. A heavy rock near our planet stabilized Earth's rotation, and the gravitational interaction with the giant debris caused our core to heat up. In addition, the asteroid brought a lot of water to Earth. Such a collision is extremely unlikely. It's like winning the lottery, many times in a row. But so far, we have no reason to believe life in outer space exists. Just as we have no reason to believe that there's no advanced civilizations in the universe, except for ours.
A powerful burst of gamma radiation lasted a mere half second, but it released an enormous amount of energy. It was more than our sun would produce in 10 billion years. This brief flash lit up the whole sky. Afterward, a much softer and more long-lasting glow replaced it. Astronomers examined the phenomenon with X-ray, radio, optical, and infrared waves. It turned out that people had finally seen a newborn magnetar for the first time ever. It was likely formed after two neutron stars had merged. It resulted in a kilonova, one of the brightest and largest stellar blasts. Its light finally reached our planet on May 22, 2020. Imagine a massive star, at least 5 times the mass of our sun, reaching the end of its life. It might be because it's run out of its nuclear fuel. If it happens, the star starts to cool off. The pressure inside drops, and the gravity starts to squeeze inward. And then, more than 1 million times the mass of our planet collapses within 15 seconds. It happens so fast that an enormous shock wave causes the outer part of the star to blow up. It produces a blinding burst of light. This powerful blast is called a supernova. What's left behind is an incredibly dense core with a huge cloud of hot gas, called a nebula, expanding around it. If the star has been massive enough, more than 10 times the size of the sun, it's likely to turn into a black hole. If not, it turns into a neutron star. It's basically a giant nucleus, the central part of an atom. These stars are mostly made up of neutrons and are rarely larger than 20 miles across. For comparison, our sun is almost 865,000 miles across, which is 109 Earths put side by side. But don't let this relatively tiny size fool you. Any neutron star is at least 1.5 times heavier than our sun and has an intense magnetic field. If you scooped just a teaspoon of this star's insides, this matter would weigh more than 1 billion tons. It's so dense that it makes neutron stars some of the most extreme objects people know about. The next stop is the black hole itself. When two neutron stars merge, they most often create a new, much heavier one. Within milliseconds, or even less, this star collapses into a black hole. But the astronomers who examined the flash of light recorded in March think there might be another outcome. They're almost sure they saw something never observed before: the birth of a magnetar. That's a rare form of a neutron star with an ultra-strong magnetic field. It's 1,000 trillion times stronger than our planet's. This field is also so powerful, it heats the star's surface up to 18 million degrees Fahrenheit. To put it simply, magnetars are the most powerful magnets in the universe. Their magnetic fields can seriously mess with the neighborhood. Atoms, unlucky enough to get close to such a star, get stretched into pencil-thin lines. If you somehow found yourself several hundred miles away from a magnetar, it would end badly for you. The magnetic field would first disrupt your bioelectricity. It means that your nerve impulses wouldn't work anymore. Even your molecules would change under the influence of the star's field. In the end, you'd pretty much vanish. If a magnetar flew within 100,000 miles from our planet, it would wipe out all the data on every single credit card in the world.
You're driving to your sister's house when all of a sudden the sky changes. The cool weather becomes scorching hot in a matter of minutes. People who were going for casual autumn strolls have now taken off their jackets and are sweating. People who were planning on going for a weekend ski trip have canceled their plans at the last minute to head to the beach. It was sunset, but the sky has become as bright as day. You fish out your sunglasses and continue driving. Nothing seems normal, but people don't seem to care. You put on the radio and hear everyone panicking about the sun. Nothing is cohesive. They're jumbling up their words and saying a gazillion things at the same time. You take out your phone and see what's happening on social media, and it's all the same thing. Nothing is comprehensible. It's just people talking about how the sun is getting closer to the earth. Footsteps are clacking along a quiet hallway. A man dressed in a sharp suit is making his way to one of the most important meetings of his life. Adam walks through the meeting room while everyone is waiting to hear what he has to say. As the head astrophysicist, it's Adam's responsibility to figure out what is happening and not let the public know what's going on. Otherwise, the whole world will succumb to panic and mass hysteria. which won't be good. He takes a seat at the head of the table while everyone waits for what he has to say. The room is tense and no one is saying a word. He takes off his glasses and places them on the table. Everyone is watching his every move. He takes a few files out of his folder and starts reading. His voice can command a room. My fellow colleagues, I'm afraid the worst has fallen on us. After countless hours of consistent observation and analysis, we have discovered that a piece of the sun has abandoned its orbit and it's making its way toward us. We still don't know which part of the sun, but we know that once it strikes us, we may not have an Earth to call home any longer. The tension in the room is palpable. Everyone looks at each other confused. Adam answers as many questions as he can, but he himself doesn't even have some of the answers. In a matter of minutes, the press leaks some voice recording of Adam's speech, and the world goes berserk. Back to you. You just heard a snippet from Adam's speech and aren't too convinced of its validity. Even though the sky is getting brighter by the second, there's still no reason to panic. You continue driving, and suddenly you sense an intense vibration. Your car lifts off the ground and the windows shatter. You get out and duck for cover. You saw a comet-like object strike down in the middle of nowhere, miles away. More of these objects look like they're heading toward the ground. You start your car and drive off, trying to find a place to hide. Ashes start covering the sky, which makes it even hotter than it already is. The earth is scorching. Meanwhile, traffic is piling up for people who want to escape but don't have any real place to hide. You eventually abandon your car and go on foot, trying to find a place to cool down and get away from the sun's rays. Even though ash is covering the sky, the sun is still blasting through it. You head to the woods and find a cave to cool down in. It's still hot, but at least you can calm down and figure out your next move from there. You get out your phone and try to see if there's any news updates on what's happening, but nothing seems to be updating. You keep refreshing it, but nothing works. Suddenly, you hear some people getting closer, and they order you to step outside of the cave. Adam is with the top scientists in the world, trying to figure out a solution. Everyone is presenting him with solutions, but in the end, none of them are achievable. They've spent hours in the office, but with each passing minute, the sun is getting stronger and the sky is getting brighter. It feels like nothing can be done until Adam has an aha moment. He calls for everyone's attention and asks for the extra people who are not contributing to leave the room. He mentions that they need to launch a rocket into space that can divert the large mass heading toward the Earth before it breaches the atmosphere. They only have a few hours before the sky becomes completely dangerous and unsuitable for flying. As for now, all flights around the world have been canceled. There is only a small window of opportunity to get this rocket out there and save the world. Adam summons the best engineers he can find to adjust the rocket and the astronauts who will volunteer for the mission. They go into quick basic training and start planning for the next steps. After many briefings, they're ready, but they only have one shot at diverting the large object. The astronauts are ready and begin to enter the rocket. Suddenly, you pop up out of nowhere, dressed in a spacesuit. You're one of the prominent astronauts for the mission. Those people who found you in the cave were from NASA, trying to recruit you for the mission. You meet with Adam, and he quickly briefs you about your role. Because the mission is very last minute, there wasn't even time for Adam to sit with you and give you the proper training or brief. You enter the rocket and take your seat. The engineers and scientists gather around to make sure that everything is in order before takeoff. The large object is getting closer, and if the rocket is delayed, then it'll melt when it reaches the final part of the mission. You're strapped in, and the rocket starts rattling. All systems are in order. 3, 2, 1, blast off. The rocket picks up and shoots into the sky. There are extra layers of visor shield protection, since it feels like you're getting closer to the sun. After a few minutes, the rocket leaves the Earth's atmosphere and is at the forefront of the large object. The rocket suspends itself in a certain strategic position, waiting for the right time to swat the object out of the Earth's trajectory. Meanwhile, everyone back on Earth is hiding in bunkers when the loose debris strikes. A cleanup team will be ready to get rid of the space rocks that will be scorching hot. The bunkers are equipped with food, water, and electricity in case they have to remain underground for a while. Only a few minutes left until the moment comes. You press a button and get ready to deploy a large spike that's as long as the Statue of Liberty. The spike is kept on a stand that's attached to the rocket. It will fire the spike like a bow and arrow and shoot it straight through the large object, breaking it before it melts. There's less than 1 minute before impact. The arrow is stretched and released. The tip of the arrow has a titanium drill that will continue drilling through the object as soon as it hits. The arrow is released and shoots through space, breaking little pieces of space objects along the way. As it speeds through, it finally hits the large object and drills through it. But nothing seems to be happening. The drill is barely getting through the center. Luckily, Adam had already thought of a backup plan. The rocket, still suspended in its spot, fires a laser where the spike is to speed things up. The laser starts melting through to get to the core. The object is getting closer and is speeding up. The object still hasn't broken into pieces yet. Less than 2 minutes until impact, and everyone is running out of options. Adam has one last trick up his sleeve. He orders everyone to evacuate the rocket and move to the backup pods. He wants to put the rocket on a straight collision course with the large object. There's too much confusion. Everyone, including you, quickly heads to the pods and ejects to a safe distance. These pods won't float around in space since they have pressurized air that allows the pods to move in whatever direction the driver wants. Everyone shoots out of the rocket while it goes full speed at the object. They're both going, heading for each other at full speed. There are only a few seconds until impact. The whole world is watching. This rocket is now the only hope there is to save everyone on Earth. The rocket starts melting before impact, and suddenly, a large shockwave ripples through the sky. The rocket was able to break the large object into many pieces. The problem now is the smaller debris falling onto Earth. But since everyone is in bunkers, they're safe. Adam and his colleagues celebrate. You and the rest of the astronauts are safe and make it safely back to Earth. The next phase for everyone on Earth is to rebuild everything that was destroyed. People will have to start everything from scratch. But this is only the beginning of a new chapter in life.
At some point in its long and very interesting history, our dear planet Earth was sort of snoozing, just doing its planetary thing, spinning around the sun. And then, bam, life starts getting fancy. Plants and animals start strutting their stuff, showing off their complexity. Fast forward a bit, about 65 million years ago to be exact, and a cosmic disaster strikes, or at least that's what we presume. An asteroid probably smashed into Earth, wiping out the dinosaurs and other big animals. We can't pinpoint specifics about the asteroid, but we do know that it was extremely large and it crashed into our precious planet, creating a dusty mess that settled everywhere. You can still find remnants of that dust layer in sedimentary rocks today. If you dig beneath it, you'll uncover a whole bunch of fossils. These prehistoric creatures were living it up before the asteroid crashed the party. Think of it as the planet going on a cleaning spree, leaving a bunch of empty spaces waiting to be filled. And guess who took the opportunity? Mammals! These furry little critters were the ones to rise to fame. But why is it that this disaster became such a great opportunity for mammals? It's pretty simple, actually. With no big bullies around, they grew, multiplied, and had a population expanse. All kinds of mammals joined to fill in the blanks. Primates, rodents, basically, the whole furry gang. We're talking about placental mammals, marsupials, and even egg-laying mammals, adding some serious variety to the mix. We like to think of primates as our closest relatives here on Earth. What's their story? Well, around 63 million years ago, just a couple of million years after the dinosaurs' final dance, the primates decided it was time for a family reunion. They split into two groups, the dry-nosed primates, who became the cool monkeys and apes we know today, and the wet-nosed primates, who went off to become lemurs and aye-ayes, hey-hays. The fun didn't stop there. About 58 million years ago, the dry-nosed primates began their own little mission. One special guest called the tarsier, arrived on the scene, featuring big eyes that were perfect for late-night shenanigans. This tarsier took a different path from its primate relatives, embracing its unique niche and evolving separately. To this day, the tarsier is the only primate that feeds exclusively on meat. These little guys have a taste for insects, small birds, rodents, and even lizards. But that's not all that makes them unique. Their eyes are twice the size of their brains. Also, their heads can do a full 180-degree spin, just like an owl. Because of their features, the tarsiers are the true kings and queens of the night. With their superpower of ultrasonic tracking, they can spot their prey instantly. Plus, their legs and feet are like springs ready to launch them into action. They've got this special ankle bone called the tarsus, which gives them those epic leaping skills. Hence the name, if you were wondering. But let's leave these little critters to rest and get back to our story, shall we? About 55 million years ago, the Earth cranked up the heat, literally. This sudden hot pod was a bit too much for many deep ocean dwellers and plants to handle, and they bid their farewells. But hey, every goodbye is an opportunity for something new, right? The oceanic mammals known as cetaceans, saw their chance and took it. They splashed into those empty niches, becoming the rulers of the sea. In this category of creatures, you can find the blue whale and the dolphin. A special primate guest made an appearance around 47 million years ago. Scientists now affectionately call the fossil of such a creature Ida. This little wonder caused quite a stir, initially hailed as the missing link in human evolution. But here's the hilarious part. It turned out Ida was not one of us dry-nosed primates, but a cheeky wet-nosed one. Moving forward to 40 million years ago. This is when another big event happened in the primate world. The New World monkeys, our distant cousins, decided to take a different path and branch off from our lineage of Old World monkeys. They packed their bags and set off to conquer South America, where they're still living it up today. What's the difference between the two, you might ask? Well, one crucial thing that sets them apart is the fact that the Old World monkeys had nostrils that pointed downwards. Around 25 million years ago, another troop of apes entered the scene, and these guys had something special, the lack of a tail. These unique creatures would go on to become our closest relatives. We're talking apes and great apes, the cool gang who share a whole lot of genetic similarities with us. The first ape to break free from the monkey madness was the gibbon. About 18 million years ago is when this little acrobat swung into the picture. A few million years later, the great apes made their grand entrance too. Orangutans were the pioneers, venturing into the wilds of southern Asia. We're getting closer and closer to the present. It was 7 million years ago when the great apes took a major fork in the evolutionary road. One path led to our ancestors, the future Homo sapiens, and the other path led to chimpanzees and bonobos. These two primate branches remained united for a few million years before finally going their separate ways. 5.6 million years ago, a game-changing ape called Ardipithecus made its way into our evolutionary history. It had a special talent, bipedalism. That's right, this was one of the first apes to walk on 2 feet, probably making its primate buddies raise an eyebrow or two. The real showstoppers, however, arrived around 4 million years ago, the Australopithecus crew. These were the earliest members of the Hominina hominina subtribe, our tribe. What made them so special? Well, probably the fact that they brought some serious tools to the game. Stone tools, to be precise. It seems that at some point in their evolution, these clever primates started using stones to make their lives easier. Now here comes a crucial turning point in our story. About 2 million years ago, our ancestors faced a food shortage. Survival of the fittest was the name of the game, and 2 strategies emerged. Group 1 went for stronger jaws, allowing them to chomp on tough foods like nuts. Group 2 had a different idea. They opted for weaker jaws, but bigger brains. They wanted access to a wider range of food options. Obviously, the bigger-brained group took the prize. And here's where our gang comes into play. Around 2.5 million years ago, a type of primate also known as handyman made its mark on history. These clever beings had larger brains and knew how to put those neurons to good use. About 1.9 million years ago, a new star emerged, Homo erectus. These creatures not only walked upright, but also had brains that were almost twice the size of the handyman's. They took the world by surprise, becoming the first of our direct ancestors to venture out of the African continent. They even knew how to tame fire. Approximately 700,000 years ago, the world witnessed a culinary revolution. The earliest evidence of cooking appeared. And around 500,000 years ago, our ancestors decided it was time to become a bit more fashionable, donning the first evidence of clothing. Our very own species came to be just 300,000 years ago. Told you we were late to the party. But the world was never the same after the appearance of Homo sapiens, the anatomically modern humans. Alongside our other relatives, we emerged, ready to conquer the world with our innovative minds and complex societies. The exact path of our evolution remains a bit of a mystery. But what we do know for sure is that Neanderthals joined the party around at some point too. As Homo sapiens flourished, so did our capacity for language. Modern speech is believed to have emerged almost hand in hand with our species. We started expressing ourselves, sharing stories, and shaping the world with our words. So, there you have it. It took 13.8 billion years of cosmic history for humans to make their entrance. Think about it. 99.998% of the time since the Big Bang, we weren't even around. Our species, Homo sapiens, is the toddler of the Earth's family, existing for just the tiniest fraction of the universe's timeline. Yet, in this blink of an eye, we've managed to unravel the entire story that led to our existence. The story won't end with us. It's an ongoing saga, still being written with every passing moment.